Good evening. We are starting part 2 of chapter 20, and we're going to pick up by looking at fossil records that we have access to, and specifically the Paleocene-Eocene thermal maximum, which we'll short to PETM, P-E-T-M. That was about roughly 56 million years ago. And what we have done, what scientists have done, they've looked at sedimentary rocks, sediments from the ocean, and by looking at these, it suggested a massive increase in CO2. And the thought of that massive increase in CO2 was the breakup of the supercontinent Pangaea. And I'll show you a little brief YouTube video on Pangaea.
Continental drift. Let's travel back in time and watch continents move. Moving back in time, the Himalayas and Mount Everest disappear as the collision between India and Asia is reversed. Climates are changing. Australia joins Antarctica as India approaches. Going back 150 million years, the continents are joined in 3 large pieces. South America and Africa are on one landmass. India, Australia, and Antarctica form a second. North America, Europe, and Asia make a third. 225 million years ago, the supercontinent Pangaea exists. Let's watch this movement as it occurred going forward in time. As Pangaea splits into 3 large pieces, the Atlantic Ocean starts to form. India starts its race to collide with Asia. As the continents take their current locations, India and Asia collide, and the Himalayas and Mount Everest appear. What is next?
So because of the large breakup of Pangaea, what we ended up seeing was quite a bit of CO2 released into the atmosphere. And the thought is that this increased global temperatures by anywhere from 5 to 8 degrees Celsius. And there was very little glacial ice present at that time. Now, if we look at recent temperature increases, we actually see a much steeper rate of the increase in temperature over a much shorter period. There is actually a graph I'm going to show you. Hold on just a moment. See if I can grab that. This actually shows the rate of warming compared to the PETM time. And so what we look at here on the x-axis, we have years since greenhouse gas emissions started. So we go back 500 years all the way back to 20,000 years. And then on the y-axis, we have the rise in temperature in degrees Celsius. And so what we see from the breakup, we talk about it, basically it took about 20,000 years to reach an 8 degrees Celsius rise in temperature because of the breakup of Pangaea. But if you look at the amount of CO2 or carbon dioxide released since the Industrial Revolution in the late 1700s, we see we have that 8-degree temperature increase in a relatively short period of time. They're actually extrapolating this out to 2400 on that. So, warming, we have been warm. We have been 8 degrees Celsius warmer in the past. It's just taken a lot longer time for that to occur. And so what we're beginning to see in the records is a rapid increase, or there's the anticipation, if we look at global climate models, of a rapid rate in change in temperature over a relatively short time period. Now, if we look at glaciers and sea ice, because they actually play a role in global climate change. We'll talk a little bit about this. Techniques of studying changes of glacial ice in Antarctica and Greenland have improved quite a bit, in part due to satellite remote sensing and the use of tools such as radar and laser signals. And what we actually find in what we call an ice core, let me just take a moment here at this point and show you a couple of brief YouTube videos on ice cores. They're very interesting. It's a way of looking back into the past to infer temperatures based upon concentrations of CO2 and methane in the ice cores.
Hi, Alex here. Is climate change really human-made? There's been a lot of research and reports published over the years, and I don't blame you if you don't want to read it all. So here's what we know for sure in 3 minutes. Let's get drawing. It all started in 1998 when an ice drilling project was undertaken in the Russian Vostok station in Antarctica. The project yielded the deepest ice core ever recovered, giving access to ice that was 420,000 years old at a depth of 3,623 meters. It supplied data about atmospheric composition and climate through 4 climate cycles. So here is how it all works. The formation of the glaciers results from the transformation of water into ice. During this process, which can last thousands of years, sediments, air, and rocks are stuck into the ice, making millions of layers, one above the other, in chronological order. Over the time, the glacier becomes a 1,000,000-page history book with the last chapter on the top. The deeper you drill, the older the compounds are. The ice core gave access to climate data, including local temperature, precipitation rate, wind strength, etc. But also, and this is what we are interested in here, the ice core provided direct records of past changes in atmospheric trace gas composition thanks to their entrapped air inclusions. Then, it was possible to determine the levels of carbon dioxide, CO2, and methane, CH4, at a given time. So, here is what global temperature and atmospheric concentrations of carbon dioxide and methane look like over 4 climate cycles, 420,000 years. So you can clearly see the 4 climate cycles, and you also see that they have very similar spikes and patterns. There is clearly a relationship between temperature, carbon dioxide, and methane. The upper and lower boundaries of the 3 variables are tightly constrained, which is typical of a self-regulating system. Our body is also a self-regulating system, and thus something similar in a way. When you exercise, your body sweats as a way to regulate its temperature. Well, on Earth, when concentrations of carbon dioxide and methane go up, global temperature goes up too. Now, here's what happened with the concentration of atmospheric CO2 since 1960. It increased by about 70 parts per million, that is more than 1 part per million each year, indicating significant human perturbation in the self-regulating system of Earth since the beginning of the Industrial Revolution. As this concentration is now way over the upper boundary noted during the last 420,000 years, and as the Earth seems to be a self-regulating system, well, we can expect the global temperature to increase as well, and we are already seeing this worldwide. Since the Vostok research was published, more recent ice cores were performed by the European Project for Ice Coring in Antarctica, the EPICA. They provided data for the last 800,000 years and confirmed the findings in Vostok. So, as the Intergovernmental Panel on Climate Change simply puts it in their 2013 report, human influence on the climate system is clear, and we can safely say that we, human beings, are responsible for climate change. So please subscribe to learn more about sustainability through short animation videos, and thank you for watching.
Inside of this ice core is trapped the environment from about 50,000 years ago. One of the things you can easily see in this ice core are small bubbles. That's the atmosphere trapped at the time that this particular ice was formed.
Scientists have only been deciphering the pages of these frozen books for about 40 years. Geoscientist Jim White unlocks their secrets at the Institute of Arctic and Alpine Research in Boulder, Colorado.
We can crush it up. We can remove the air that's inside of here and find out how much CO2 is in the atmosphere, or how much methane or other greenhouse gases were in the atmosphere at that time that this ice core was formed. So this ice core is a wonderful book, if you will, a recorder of the past environment.
He says this old ice can bring new understanding about global warming.
So it's not just that the past tells us what happened, but the past gives us some clues about what could occur in the future. One of the neat things about ice cores is that in areas where you have lots of snow accumulating every year, you have very detailed time records. Greenland is a place that has lots of accumulation. So we can look at year-by-year changes 20,000, 30,000, 40,000 years ago.
White's recent analysis of Greenland ice cores, a National Science Foundation-supported project, has revealed some important clues about rapid climate changes near the end of the last ice age about 11,700 years ago. At the time, there was a 22-degree Fahrenheit temperature spike in just 50 years in the Northern Hemisphere. When you're talking about major changes to the Earth's temperature, 50 years is practically the blink of an eye. The triggers for those ancient, dramatic climate changes: atmospheric circulation, like the jet stream, ocean circulation, like the Gulf Stream, and fluctuations in levels of sea ice.
Where are those trigger points in the modern climate system? Is it sea ice, which is disappearing rapidly? Is it ocean circulation? Is it atmospheric circulation? Or is it some combination of those three? I would say we're still flying blind when it comes to whether or not a rapid change is on its way.
More and more data from ice cores is expected to improve computer models for predicting future climate change. That's vital, said White, so the planet can be prepared to adapt.
Greenland contains something in the neighborhood of 20 feet of sea level rise, where the entire Greenland ice sheet to melt, that would inundate, drown major cities like Miami and Houston and New Orleans, Oakland. It would be, all around the world. So it's important to recognize how much ice is up there.
There's a certain rugged and spirited nature to the scientists who work in temperatures around minus 20 Fahrenheit. This time-lapse video is from the drilling shelter at the West Antarctic Ice Sheet Project. After the cores are drilled and retrieved, they are painstakingly prepared for study at more than 24 universities, with an occasional break for some calisthenics in the cold. Ice cores from the Antarctic and Greenland are flown to the National Ice Core Lab, a National Science Foundation facility near Denver. Many then make it to White's lab at the University of Colorado.
We measure about 10,000 samples a year, so we have to take some fairly detailed records in this ice core. There's a thermometer that lurks within the ice. This one is based on the ratio of heavy hydrogen to light hydrogen. The more heavy hydrogen you have, the warmer the cloud was that made the snow.
Like all those crime scene investigators on TV, these experts determine the what, where, and when, but with evidence from eons ago.
This is a system that will analyze carbon monoxide concentration and isotopes and ice cores.
Well, this instrument here is measuring the hydrogen isotopes of methane. And what that tells us about is where the methane comes from. Is this coming from the tropics? Is it coming from polar regions? The evolution of the ice core analysis has really been remarkable over the last 40 years or so. As we say, every time we measure an ice core, we find new information.
Information that could make a difference in our planet's future. For Science Nation, I'm Bruce Burghardt.
So as you can see from the two YouTube videos, we look at isotopes of oxygen and hydrogen to infer temperatures, within the bubbles of air that were trapped by the ice. So it is a fascinating way of looking back into history. Ice cores also contain different types of chemical materials such as volcanic ash and dust. And we know that both volcanic ash and dust tend to have a very high albedo when they're up in the atmosphere, and so they reflect quite a bit of sunlight, incoming shortwave radiation from the sun, back out into space, which would begin to decrease temperatures. So these will provide additional insights into possible causes of climate change. It certainly gives us an idea. However, how ice changes on the Earth's surface occurs in many different ways. It just doesn't have to do simply with temperature changes, but it can have to do with atmospheric circulations. That change in atmospheric circulation or winds can cause problems in terms of ice. But the major concern is that global warming may lead to a decline in the amount of water stored as ice. And observations basically suggest that there has been a large net loss of glacial ice in both Antarctica and in Greenland. And in fact, if we look at this particular graph here, this figure here, notice that it shows the North Pole. So we're looking at the northern hemisphere and the southern pole down here in the southern hemisphere. And notice up here you have a legend that goes from 77, so that's 1977, all the way through 2005. And so what they looked at was the change in the average thickness of glaciers in different locations, both in the northern hemisphere and in the southern hemisphere. So for example, in the South Cascade, which is number one up here in the Washington State area, since 1977, we've seen a decrease in almost 28 meters of the thickness of glacial ice in a span of 28 or 29 years from 77 to 2005. If we look at this, it's called Place up in Canada, not far from the Cascade area, that also shows a decrease in the average thickness, and in fact, even more, down to 33.6 meter net loss of thickness of ice. And then if we look at just all of these, notice there has been a net loss of ice, except for number 8 here up in Norway, where we've actually seen an increase of 13.8 meters. However, the rest of these, both in the northern and southern hemisphere, all show decreases. And in fact, the largest decrease is about almost 36 meters over in Italy, number 12, showing right here. So there's definitely loss of glacier ice occurring in both the northern and southern hemisphere. And in fact, this particular location here shows how ice has retreated since 1941. So you see the glacial ice here, and now what we have is a lake, and the glacier has actually retreated quite a bit in the 64 years that is shown here. And there are other examples that you can see of glacial retreat. All you have to do is just Google that, and it'll show you different areas throughout the world where there has been noticeable glacial retreat, especially in the last 100 years. However, not everything is retreating. In fact, the central ice cap on Antarctica down in the South Pole is actually growing. And believe it or not, this is consistent with the prediction of global climate change models. Because as the Earth warms, we begin to get more evaporation, which means we begin to add more water vapor to the atmosphere. With more water vapor is a moisture source for storms. And so, based upon global circulation patterns down in the Antarctic region and enhanced water vapor, enhanced moisture, we begin to get more snow falling. However, that's new snow, and there is a difference between new snow and older ice. So you have new ice and older ice. New ice is very thin and can break up rather easily. So while we are beginning to thicken that area, again, it is more of the new ice. However, if we look at Greenland, the rate of melting has doubled since 1998, so a relatively short period. This particular picture here shows the extent of glacial ice up over the North Pole, and we see that the median September value from 1953 to 2000 is shown here. By the time we look at 2005, notice how much the ice has retreated in a few short years. And there are even some numerical climate prediction models that say by 2030, for most of the summer, we will completely remove the glacial ice up in the Arctic. And this has dire consequences. Keep in mind that snow and ice has a very high albedo, almost 95%. And so think about that. Without the ice up here, more incoming shortwave radiation from the sun is being absorbed, which is heating more of the oceans, which releases more CO2. So the oceans can't hold as much CO2 as they begin to warm up, so it begins to give up. Oceans are a great sink of CO2. It stores a lot of carbon dioxide. However, if it begins to warm, it will release that carbon dioxide. So let's talk about some of the potential rates of global climate change. Let's put some numbers on this. We know that global surface temperatures, now we're talking about global, the entire globe averaged, has increased by about 0.2 degrees Celsius per decade in the past 30 years. That doesn't seem like a lot, but that's over 0.5 degree Celsius just in the past 30 years. And in fact, the period, the last decade, was the warmest on record. And if we look at how we continue to put out CO2 into the atmosphere, it's estimated by 2030 the concentration of CO2 will double what was in our atmosphere back in the 1700s. We also have this term called polar amplification, and that's what I was just getting to when I was talking about the sea ice melting here. It's basically as it melts, the solar energy, the incoming energy from the sun, is now being absorbed by the oceans and not bounced away or reflected back into space. And so we see that more vegetation and water being exposed to sunlight results in enhanced warming. Now let's look just briefly at potential changes in river flow and sea levels. We know that the melting of the ice itself and reduced snow cover are expected to increase in the 21st century. Now, over in the desert southwest, parts of California and Arizona, they depend upon snow melt. That's where they get most of their water, is from that snow melt up in Colorado. And so if we have decreased snow, which we have had over the last few years, so the temperatures increase, less precipitation, and so their source of water in the desert southwest will begin to dry up. And so they've already seen reductions in water availability. And keep in mind, there are some hydropower plants out there. They use water to produce electricity and energy. That's going to have a negative impact as well. And also the patterns will change with varying effects on the reservoir levels and irrigation systems. So you can see that global climate change begins to impact a lot of different areas. Let's talk a little bit about the rise in sea level. Since the last ice age back in the 1400s, sea level has risen on average about a foot per century, and there are estimates that global warming could double this. And you saw just in the YouTube video just a few minutes ago, it talked about if the ice in Greenland melts, the sea level will rise and will inundate areas such as Miami, Houston, San Francisco, although they didn't mention it. Manhattan also and Long Island would be inundated. I've also read about parts of the Netherlands. They already sit pretty low to begin with. They would be completely inundated. And so this could create a lot of issues, such as threatening island nations. Your textbook talks about a particular island that it would not take a lot of melt at all to actually inundate this island. And think about it like this. More and more people across the globe are living in lowland areas and living by seas, especially countries with affluence. They want to live near coast. And so there could be a lot of economic damage, also a redistribution of population. We talked about population dynamics. And so we begin to move large populations, and that causes stress not only on transportation but also on food. It's just one domino after another. Now, when we talk about losing coastal wetlands, we notice that there's a lot of biodiversity in these areas, not only in the ocean. We've talked about aquaculture, but also the wetlands. There are so many things that will be impacted. Here is the picture of that island that I briefly mentioned. There's not a lot of margin for error here. It would not take a lot of melting to raise the sea level to inundate these islands. Now, I've kind of hinted at changes in biological diversity, but let's get right into it. The Interpanel Climate Change, I'm struggling over this part. I've always the IPCC, the Intergovernment Panel of Climate Change. It's a group of scientists that have gotten together at least since 1995 that puts out reports, I believe, every 2 years as they study global climate change. And what they've said that anywhere from 1 to 2% to almost a fifth of species looked at so far could be marked for extinction if we just warm the climate 2 to 3 degrees Celsius above pre-industrial levels. We're already approaching 1 degree Celsius over pre-industrial levels. And this is a global average, which makes the warming even more catastrophic. Your textbook uses an example of birds that have nested on Cooper Island for years. For instance, they talked about when they begin to nest and have babies, and the food that they feed to their babies, they have to travel distances. They can travel up to about 20 kilometers, which is roughly 12 miles. But with the way that we're beginning to see melting of ice, this increases the amount from their feeding grounds to where their nesting grounds are at. And so that creates an issue. There's not food available. They have to go further out. And so that is one example of a change in biological diversity. Another one I've read about before also, Mount Kilimanjaro. They talk about with the warming, the mosquitoes. So there are some villages and towns built at different elevations on mountains to avoid mosquitoes. So they go further up where it's cooler, a bit drier, but as temperatures begin to warm, the mosquitoes begin to migrate up the mountain. And so now those towns and villages that were above the mosquito line are now being infested by mosquitoes, which brings diseases such as malaria is one that comes to mind. Now, when we talk about changes in biological diversity, we also talk about agricultural productivity. Now, this is really something that hits really close to home. We know that here in the Midwest, we are the bread belt. portions of the U.S. Midwest feed a large portion of the globe. We export a lot of our grains to Russia, is one country that comes to mind. But what ends up happening, though, as we begin to increase temperatures, corn, we look at the corn crop, corn begins to, as it begins to biologically develop, if it reaches a threshold, I believe it's 87 degrees Fahrenheit, but above 87, then it becomes stressed, and it becomes biologically stressed and does not produce optimally. So as we begin to warm the Midwest, corn crops, what do you think they do? They end up moving northward. So as the breadbasket of America, the Midwest right now is optimal in terms of soils, in terms of temperatures, in terms of precipitation is optimal. In a warming climate, the breadbasket is going to move northward into some of the southern Canadian provinces. So the issue there, though, is that the soil there in the southern Canadian provinces are not as rich in like nitrogen and those types of chemicals that help crops to grow. So even though from a climatological standpoint, the southern provinces of Canada would seem to fit well in a warming environment, their soils themselves do not have the necessary ingredients. So that's something we have to look at as well. Human health effects. It says here difficult to forecast, but vector-borne diseases. These are diseases that are carried by, like mosquitoes with malaria. If you think about rats, mice, some of the things, the diseases that they carry. If you look at things that are along the southern U.S., animals that are along the southern U.S. that carry diseases, in a warming environment, those will begin to progress northward. And so areas in the Midwest that didn't have to worry about some of these vector-borne diseases now will have to consider that. So there are all kinds of things to look at in terms of global warming. Now, how do we adjust to this? There are two ways your book suggests. One way is we adapt. You know, we learn to live with a warming environment. It's easier said than done. Probably it's a combination of adaptation and mitigation. And one of the ways that we can mitigate the CO2 that's being put up there is to reduce the greenhouse gases. It takes quite a bit of sacrifice to reduce, because you look at developed countries, the U.S., China coming on board now, portions of Europe. We are used to a certain lifestyle, and with that lifestyle requires energy. We've talked about energy in this course. To do that, our main sources of energy right now are fossil fuels, and so as we continue to develop and third world countries begin to move into more affluent types of economic times, they're going to want to have that lifestyle as well. And so we have seen one improvement over the last 10 years. You know, coal is a source of energy that produces, or is a fossil fuel that produces energy and electricity and those types of things. Well, since we've switched over to more natural gas, some of the coal plants are shutting down, and now natural gas plants have come online more and more, especially in the Gulf of Mexico. Over the last 10 years, there have been numerous reserves of natural gas that have been discovered. Natural gas, as we know, produces less CO2 in its waste compared to coal. And so that in itself has helped to at least get us closer to a mitigation strategy. But we have to really make some severe cuts. So some of the ways that we can reduce emissions, and we talked about this in the last chapter, in chapter 19, is relying on energy conservation and the energy that we do have, making it more efficient, using alternative energy sources such as we talked about wind power, solar power, hydropower, all that, although that's becoming limited. We also talked about nuclear power. But each one of those energy sources in themselves still have drawbacks and are not as they cannot produce as much energy as fossil fuels, unless we're talking about nuclear energy. You recall we talked about roughly, what was it, about 2.2 pounds of nuclear material, and I'm drawing a blank, and I'm not sure why I'm drawing a blank. Uranium, yes. So about 2 pounds of uranium can produce as much power as many, many thousands of tons of fossil fuels. So while nuclear energy certainly is in terms of efficiency, is a much more efficient way of producing energy without the effects of CO2, there are major drawbacks to that. What do we do with nuclear waste? We talked about that. Nuclear waste, we have to put it somewhere where it doesn't get into our water tables, or there are challenges with that. The use of mass transit, greater economic incentives to companies to create more energy efficient technology. If you look at the cars over in Asia, the miles per gallon they're getting there, the standard's 35, 40 miles per gallon, whereas here in the U.S. it's half of that is the standard. And so we have to look at those types of things as well. Now, burning forests, we've talked about that to convert land to energy. That counts for roughly a fifth of human emissions of carbon dioxide. If we can reduce this by minimizing burning and protecting the world's forests. We can also practice reforestation, in other words, planting more trees, which in turn creates a sink for CO2. Another method of mitigation is to basically take carbon and pump it down into the Earth's subsurface. And so what they're finding now is basically what they end up doing is they take the CO2, they compress it until it becomes a mixture of both liquid and gas, and they inject it underground. And in fact, what they're looking at is injecting it into areas of old oil fields. Okay, we talk about oil fields that have dried up, and so they look at those types of things as sources. And so we have the potential to sequester or store away 1,000 gigatons of carbon using that. Two additional ways to promote mitigation of global climate change or global warming. One is an international agreement in which nations agree to set specific limit on greenhouse gas emissions. The Kyoto Protocol, 1997, was one, but the U.S. is not one of those nations that is participating in it. And so there are some challenges there to get nations to agree to this. But one other interesting way of doing this is a process called carbon trading. It gets economics involved and motivates companies to lower their emissions. It's actually quite creative, and I have a short YouTube video to explain that.
How does the European Union Carbon Emissions Trading Scheme work? The greenhouse gases present in the atmosphere help keep the Earth at an average temperature of 15 degrees Celsius. Without this greenhouse effect, the world's average temperature would be minus 18 degrees Celsius. Since the Industrial Revolution, large amounts of greenhouse gases are released into the atmosphere as a byproduct of human activities. Their rising concentration in the atmosphere leads to an increase in the average global temperature, which in turn disrupts our climate. In 2005, to limit the emission of greenhouse gases, the European Union decided to introduce the first multi-state carbon market. In 2015, this has become the largest emissions trading scheme in the world.
How does the European carbon market work? First, the European Commission defines an emissions cap for a certain time period. This cap is then divided and shared between the different market players in the form of tradable allowances. Each allowance represents the right for an industrial plant to emit 1 ton of CO2 equivalent. At the end of each period, plants must demonstrate a balance in their allowances and their emissions. They then have 4 months to return the corresponding allowances to the market authorities. For example, let's consider 2 companies which are issued 100 allowances each, corresponding to an emission volume of 100 tons of CO2 equivalent. If at the end of the year, Company A has emitted 120 tons of CO2 equivalent, it will have 4 months to buy the excess allowances from the market, or it may purchase offset credits. The latter represents emission reductions achieved by other geographic zones or in other sectors. Beyond the 4-month period, if the company is not in compliance, it will have to pay a fine and provide the missing allowances. Conversely, if Company B only emits 80 tons of CO2 equivalent, it can bank the excess 20 tons for use in future years or sell them to other companies. The European carbon market covers almost 50% of European CO2 emissions and includes almost 16,400 of the most polluting production facilities in the energy and industrial sectors. By 2020, the target is to reduce greenhouse gas emissions by 21% compared to 2005 and by 43% by 2030. This will be achieved by setting an emissions cap, which will be lowered each year until 2030.
How does the carbon price influence the business strategy of companies? Setting a carbon price is meant to help incentivize companies to reduce their CO2 equivalent emissions. The company must decide what is the most economical option in the long term. Should it compensate for its emissions by buying allowances, or should it invest in low-carbon technologies now? If a company anticipates that the price of carbon will be lower than the cost of reducing its greenhouse gas emissions through technology, then it will most likely prefer to buy allowances or offset credits. If the opposite is true, it will prefer to invest immediately in energy-efficient technologies or in renewable energies, or both. That is how the carbon market supports the development of clean technologies, on the condition that it has a strong carbon price in the long term.
I'll just briefly touch on some international agreements. One of the first ones was in 1988. That took place in Toronto. They discussed limiting greenhouse gases. In 1992, the Earth Summit in Rio de Janeiro talked about a general blueprint for reduction of global emissions suggested. However, the U.S. thought it was not cost effective, and there were no legally binding limits set. So in these first 2 meetings, these 2 conferences, there is discussion on limiting emissions. Then we moved to 1997, and I mentioned Kyoto, where there was actually legally binding limits that were discussed, and an agreement was reached in principle. The U.S. actually, although they did not sign at the Kyoto Protocol, they did agree to cut 7% below 1990 levels. However, there were a lot of scientists out there at the time that recommended cuts of 60 to 80%. It actually became a formal international treaty in 2006, but to this date, the U.S. has not signed on. So, let's just summarize a few things here that we've talked about in Chapter 20. We talked about the atmosphere itself. We talked about the atmosphere being a dynamic system, in other words, constantly changing. There are a lot of chemical reactions that occur, that take place in the atmosphere. And we also briefly talked about atmospheric circulation taking place on a variety of scales that help to produce the world's weather and climates. And we also know that nearly all the compounds found in the atmosphere are produced primarily by biological activity or affected by life itself. We've also talked about major climate changes throughout the Earth's history. We've talked about the past 1,000 years. We've had several warming and cooling trends that have affected civilizations. And even during the past 100 years, we've talked about a rise in temperature, surface air temperature, by almost a degree Celsius. And in fact, about a half degree of this has actually occurred just in the past 50 years. So we are certainly accelerating this. We talked about greenhouse gases, water vapor being the most important greenhouse gas. And we talked about in a warming environment, there's more water vapor produced as more liquid water is evaporated, which leads to additional greenhouse gases. We talked about CO2, methane, nitrous oxides, and CFCs, the role that they play as well. However, since the Industrial Revolution, anthropogenic causes, in other words, human activity, has added substantial amounts of CO2, methane, and CFCs to the atmosphere. And recall what I said about CFCs earlier. They're very stable compounds, and they will last in the atmosphere up to a century. So even though we don't put nearly as many CFCs up there as we did maybe 20 to 30 years ago, what we did put up there is still going to be up there for another half century. We briefly talked about climate models, and we looked at a scenario of doubling the amount of CO2 concentration in the atmosphere, and this means a global temperature increase. They're projecting of 1 to 2 degrees Celsius. Now, again, I point out, that does not seem like a lot, but when we're talking about average global temperatures, there are some regions, like in the Midwest, could be 4 to 5 degrees Celsius. And in fact, globally, by the end of this century, by the end of the 21st century, we could be approaching 5 degrees Celsius increase. Again, I'm not meaning to sound the alarms because these are global climate models, and there's a lot of the parameters that exist in nature that we cannot account for in a global climate model. But even a 1 to 2 degrees Celsius increase will have significant impacts, not only to climate, but also to our biodiversity. We talked about the feedback processes, both positive and negative, that can occur from there. We've also looked at concerns such as global climate warming leading to a rise in climate patterns. In other words, an increase not necessarily in precipitation, but the intensity of precipitation. Also the intensity of storms such as hurricanes and tornadoes and those types of things. We've also mentioned about a rise in sea level with the melting of glaciers and even the change in the biosphere that we have here on planet Earth. And potential threat from future warming, as in the medieval warm period, is the occurrence of droughts that would severely impact the world's food supply. And so finally, in this part of the chapter here, at the end of the chapter, we need to, it's a combination of learning to live with these changes, but also attempting to mitigate emissions by reducing emissions of greenhouse gases through creative ways.